All right, so one of the advantages of Hall's marriage theorem is that it gives you ways to determine if there's a bipartite matching that saturates a certain subset of vertices. And what I mean by that is you either give me the matching or you give me a set whose neighborhood is too small. So Tutt's theorem is a generalization to arbitrary graphs. So now you're looking for a perfect matching. So either you can give me a perfect matching and I can verify that it actually is in fact a matching, or we want another condition. If there is no matching, we want something we can check. And so it can't be neighborhoods. It turns out to be something different. So it's a similar result. We still talk about subsets, only now the inequalities go in the other direction. We want the size of the set to be at most a certain number. And in this case, instead of talking about neighborhoods, we're talking about odd components. So given a graph G, an odd component is a component of odd order. And so O of G is going to be the number of odd components. And what you want is for every set S, when you delete it from the graph, the number of odd components is at most the size of S. So we're going to refer to this as Tutt's condition. We're going to prove is that a graph has a perfect matching if and only if Tutt's condition holds. So if your graph did not have a perfect matching, you should be able to give me an S where the number of odd components of G minus S is big. So we're going to prove this theorem, and we're going to do it in steps. And some of the steps are similar to what we did for Hall's marriage theorem. So the first step is to prove that if you have a perfect matching, then your graph satisfies Tutt's condition. So that's proving one of the directions in the biconditional. So then we just have to prove the other direction by induction on the size of the vertex set. And so one of the cases is similar to what we did for Hall's marriage theorem, namely that if there's the Tutt's condition holds with strict inequality for every proper subset S, then we're going to show that you can take any edge and extend it to a matching of the entire graph. Namely that if you remove the endpoints of any edge, the resulting subgraph also satisfies Tutt's condition. So by induction hypothesis, you can find a maximum matching, a perfect matching in this graph, and then just add the edge xy. The other two steps are a little harder. So it turns out to get the rest of the proofs to work correctly, we need to prove some sort of parity condition, assuming that the number of vertices are even. For every subset S, we need to show that the size of S and the number of odd components have the same parity, which means they're either both even or both odd. And that turns out to be a rather technical point we use for step 4. And step 3, it turns out. So step 4, as we're going to see, is like Hall's marriage theorem. You're dealing with the case that there's a proper subset where the size of the set is equal to the number of odd components. However, we see that our version of step 4 is going to be a bit harder. So for one, we need to pick the largest S, where you have equality in the Tutt's condition. Then we need to show several different results. First, we need to show that all the components of G minus S happen to be odd. Then we're going to show that for any of these odd components and any vertex in the component, removing that vertex gives you a new graph that still satisfies Tutt's condition. And then thirdly, for every component C, we're going to define the set S sub C to be those vertices in S whose neighborhoods has a neighbor in C. And then we need to prove that this set has a system of distinct representatives. And why would we do such a thing? Because the idea is that we have our set S, and then we have our components, and the point is every component has to be odd. Since there's a system of distinct representatives, this means that for every vertex in S, we're going to associate it to a specific vertex and a specific odd component, which guarantees that every vertex in S is matched. And then we're going to delete that vertex from each component and then apply induction to find a perfect matching in what's left over. And then the union of all these matchings is going to be a perfect matching. So as you can see, this strategy takes some effort. So this proof is going to take some work. But the general outline is like Hall's theorem, just until you get to this step. The argument we need to do is much more complicated. So here we're going to give a general outline of the proof, assuming the previous 4 steps, and then we'll prove each of the 4 steps in detail. So first, by step 1, one of the directions of Tutt's theorem is true, so we only need to prove the converse, which is that if Tutt's condition is satisfied, then there must be perfect matching. So first we apply Tutt's condition to the empty set. So one thing worth noting is there has to be an even number of odd components, but more importantly, by Tutt's condition, this number is at most the size of S, which is 0. And so in particular, if Tutt's condition is satisfied, then there are 0 odd components, which means every component of G is even, which means the number of vertices of G has to be even. And so we're going to do our proof by induction on graphs with an even number of vertices. So we're not going to consider cases where they're an odd number. So this is a weird version of induction. We're not inducting on n, we're inducting on even integers n, which means in order to apply the inductive hypothesis, we have to ensure that we only apply it to cases where our graphs have an even number of vertices. So then the base case, G is equal to, has 2 vertices. That exercise is left to the reader. Clearly in that case, you either have 2 isolated vertices and there's no matching because you have more odd components than 0. And so if Tutt's condition is satisfied, you have only 1 component and 1 edge, and there's your matching. So let's do the inductive step. So for the inductive step, for every graph H whose size is less than G, that satisfies Tutt's condition, we're guaranteeing that H has a perfect matching. So now we need to prove that G has a perfect matching. So for case 1, suppose that for all proper subsets of the vertex set, we have strict inequality in the Tutt's condition. Take any edge in your graph. By step 3, G take away the endpoints of that edge, satisfies Tutt's condition. So by induction hypothesis, G minus xy has a perfect matching. Notice that no edge in M can have x or y as an endpoint. So when we add the edge xy to M, we get a matching of G, and every vertex in G is matched. Now we get to case 2. Suppose there exists a proper subset of vertices such that the number of odd components of G minus S is the size of S. Let's choose the largest S for which this is true. By step 4, the set S sub C, where C is an odd component, has a system of distinct representatives. We'll refer to these distinct representatives as U sub C. So by definition of S sub C, not only is there a U sub C, for each of these distinct representatives, there has to be a corresponding vertex in S such that together they form an edge. So this gives us our first part of our matching. It's a matching which saturates S. And that follows from the definition of system of distinct representatives. For every vertex in S, there has to be a representative corresponding to it, and that gives you the corresponding edge. All right. And since the number of odd components is the size of S, we see that there's exactly 1 representative in each odd component. Given a specific odd component and its representative, by step 4.2, deleting that representative from the component gives a new graph that still satisfies Tutt's condition and thus has a perfect matching. So we have a perfect matching of that component minus that vertex. Then if we glue all these matchings together with M1, we have a matching which saturates S and every vertex in an odd component. However, by step 1, there are no even components of G minus S, and so in particular, every vertex appears in this set, and thus M is in fact a perfect matching. Right, now we start proving each of the individual steps. So step 1 was that if G has a perfect matching, then it has to satisfy Tut's condition. So we can assume M is a perfect matching, and then we have to check Tut's condition. So let S be a subset of vertices, and let C be an odd component of G minus S. Then we claim that the number of vertices in M intersect the edges of C has to be even. And the point here is that each edge totally contained in C that's in the matching covers exactly 2 vertices. And since these edges are from the matching, they have to cover an even number of vertices because they have to cover distinct vertices. So that's why this is true. But remember, C is an odd component, so there has to be at least one vertex, possibly more, an odd number for sure, whose their matched edge, the other endpoint, is not in C. But remember, C is a component of G minus S, so it follows that the other endpoint has to be in S. And thus for each odd component, there's at least one edge who has exactly one endpoint in C and one endpoint in S. Since these edges come from the matching for distinct odd components, another odd component C prime, we found there's an edge with one endpoint in C prime and one endpoint in S. It must be the case that these endpoints are distinct, as otherwise you would have edges that intersect, contradicting the fact that we have a matching. And thus, for every odd component, we can associate it to a distinct vertex in S. And therefore, the number of odd components is at most the size of S. All right, now we prove step 2. Given a subset of vertices, and assuming our original vertex set has even size, we claim that the number of odd components of G minus S and the number of vertices in S are congruent mod 2. So that means they're either both even or both odd. So we're going to prove this result by induction on the size of S. When S is 0, then S has to be congruent to the number of components of G minus S mod 2. The reason why this is because in this case, since V is even, there's an even number of vertices, there has to be an even number of odd components. Because if there are an odd number of odd components, then when you add up the number of vertices, the result is total is odd, contradicting this assumption. All right, so now let's look at the inductive step. So in other words, we know it's true for all subsets up to a certain size, say K. So I didn't include this because at this point, it's supposed to be clear what's going on. So we let S be of size K plus 1. And the point is we want to prove Tut's condition holds for sets of size K plus 1. So let's let S be a set of size K plus 1. Let's take an arbitrary vertex in it. Then S take away V is congruent to the number of odd components of G minus S minus V mod 2. So we've taken our subset S and we've removed a vertex. And so this part is true by induction because S take away V has size K. So we know that these two sets have the same parity. So what we want to show is that the same is true with S originally. So what we're going to do is let C be a component of G minus S minus V that has V in it. The reason why we're interested in that case is because components that don't have V in it are already components of G minus S. What we want to show is that removing S from the graph changes the number of odd components by an odd amount. So suppose this C was even. Then once I remove the vertex from C, I'm going to create a bunch of new components. But more importantly, since C minus V is an odd number, it has to have an odd number of odd components. And so if I look at the number of components of G minus S, they were either components of G minus S take away V, or they're these new components that come from C, and there's an odd number of them. But notice when you're working mod 2, the 2k can be removed, and we already know that the number of odd components of G minus S take away V is equal to the size of S take away V when we work mod 2, and these two numbers add up to be the size of S. So then our other case is if C is odd, then when I remove V, I have an even number, and thus C minus V has to have an even number of odd components. And so then when I calculate the number of odd components of G minus S, they were either odd components we had before, or they're these 2k new odd components. Notice that C was an odd component already, so we have to subtract 1 to count the fact that we've removed C and replaced it with 2k new components. I didn't have to do that subtraction before because in the previous case C was even. And so then it's the same calculation. The 2k doesn't matter when you work mod 2. Minus 1 is congruent to plus 1 mod 2, and we get the same calculation. So again, this is a technical result, but you'll see in step 3 where we need to use it. So now we're in step 3. We're going to assume that Tutt's condition is satisfied with strict inequality for all non-proper subsets. Then the claim is that for any edge in the graph, removing the endpoints of that edge gives you a new graph that still satisfies Tutt's condition. So we're going to let S be a subset of the new graph. And then we want to count the number of odd components of G prime take away S. Well, we know these are also the number of odd components in G take away S union XY, because we already deleted X and Y. Because we're in this case with this strict inequality, we know the number of such odd components is at most the size of S union XY, which is exactly S plus 2. Notice that this plus 2 is not a plus 1, so this is different than Hall's condition. A little bit more work is needed. So this is where the parity argument enters. We know that the number of odd components of G minus S union XY is congruent to the size of S union XY mod 2. In other words, they have the same parity. So it must be the case that the number of odd components of this set is not equal to the size of S union XY minus 1, because these have opposite parity. In other words, I can try to replace this inequality with weak inequality by replacing the 2 with the 1, but then this argument tells me that if I assume equality with 1 here, then I get a contradiction. This is the strategy going on over here. We're assuming that we know that A is strictly less than B. Because these are integers, it means A is at most B minus 1. But since we want A at most B minus 2, we have to rule out the equality case, and that's what this does. And so thus we know that the number of odd components is at most the size of S union XY minus 2, which is the size of S. And thus we've seen that G prime actually satisfies Tutt's condition. And now we are in the longest case, the fourth case, which also has subcases itself. Step 4, given we're going to take the largest proper subset for which the number of odd components of G minus S is equal to the size of S. One of the things we want to show is that every component of G minus S is odd. And so this is going to be a contradiction argument. Suppose C is even. Just take an arbitrary vertex in C, and then count the number of odd components you get when you remove V from G minus S. We see then that this number is at most 1 more than the number of odd components we had before, because at the very least we've added 1 more odd component. Because of this assumption, the number of odd components of G minus S is the size of S, and so we see that the number of odd components of G minus S union V is at least the size of S union V. But by Tutt's condition, that's also the upper bound. And so when you've shown A is greater than or equal to B and A is less than or equal to B, you know A is equal to B. So we know that the number of odd components of G minus S union V is equal to the size of S union V. But this is strictly larger than S, so it contradicts this assumption that we started with the largest proper subset for which equality holds. There is a slight gap here that, this S union V could have been all of V, but if you should study that on your own and see what happens to Tut's condition in this case when you set S equal to V. There are no vertices left, so the number of odd components here is 0. And on the left-hand side, you actually have a positive number of vertices, so this condition can't be satisfied in that case. All right, now we have the second part. For any odd component of G minus S and any vertex in that component, if we remove that vertex, we get a new graph that satisfies Tut's condition. Note here that we are working in the odd component. So how do we prove this? Well, we do contradiction again. So we need to show it satisfies Tut's condition. So we look for a case where it doesn't and see what happens. So suppose it doesn't satisfy Tut's condition. Then there's going to be some t for some v. Then there exists a vertex v and a subset t such that the number of odd components of c take away t take away v is strictly bigger than the size of t. Note that c minus v has an even size, and so by step 1, we know c minus t minus v, the number of odd components, and the size of t are congruent mod 2. They have the same parity. So since we have strict inequality here, we know that the number of odd components of c minus t minus v is at least the size of t plus 2, so that we're preserving parity. And so again, that plus 2 is going to matter, because then we look at the number of odd components of G minus S minus T minus V. It's equal to the number of odd components of G minus S, minus 1, because we've removed the odd component C, plus all the new odd components we get from removing T and V from C. Now this number is at least the size of S minus 1 plus T minus 2. Here we have equality by assumption, and here we have this inequality coming from here. But we notice plus 2 minus 1 together becomes 1. So we have the size of S plus the size of T plus 1, also known as the size of S union T union V. By Tut's condition, we have the inequality the other direction. So again, we found a larger set. By adding T and V to S, we get a larger subset for which the number of odd components of G minus X is equal to the size of X. But that contradicts the choice of S. Finally, we get to this third situation, which has to do with a system of distinct representatives. It turns out our approach is going to be using Hall's theorem. So we're going to let C1 through Cj be the odd components of G minus S. Note here that the size of S has to be equal to J, because we're in the case we've been talking about, where we're assuming that this equality is true. For a given I, we're going to let S sub I be those vertices in S such that they have a neighbor in the odd component Ci. So given an odd component Ci, given our S, there's our Si. And so we want to claim that Si has a system of distinct representatives. That's our conclusion. So we want to show that Hall's theorem holds, which means precisely this condition. We're trying to prove something about the size of the union. So given a subset of odd components, we want to look at the union of the SJs coming from those components. We want to prove that the size of this union is at least the size of J, and it turns out we do that in 2 steps. First, we note that the size of this union is at least the size of the number of odd components of G minus R. That's just Tut's condition with this set R. Then for each I and J, we already know G sub I is an odd component of G minus R. That is, once you've taken this R set going on here, anything that was an odd component coming from J is still an odd component, but you might have another component that was an odd component of G minus S, but is not an odd component of G minus R. We don't care about those ones. The main point is that for the ones we do care about, they are odd components. And so we see that the number of odd components of G minus R is at least the size of J. Could be bigger. But by transitivity, we now have R is greater than or equal to J. And so R, of course, was this union. And so we satisfy Hall's theorem, the original Hall's theorem about sets. So this system does have a system of distinct representatives.